afternoon, everyone. My name is Jill Browning, and I will be your moderator for today's session. We're just at the 2 o'clock mark, and I can see that we've got some people that are still logging on. So we're going to give it about one more minute or so, and then we will get started. So thank you for your patience, and we'll get started briefly or shortly. Okay, welcome everybody to today's webinar. As I said earlier, my name is Jill Browning, and I will be the moderator for today's webinar on complete PFAS destruction in sludge using thermal oxidation. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak right now. But I do want to mention just quickly that should you have any difficulties throughout the presentation today, there are two different ways to connect to the audio. You can use either your computer or your phone lines. And then also, due to the large number of attendees on today's presentation, we have gone ahead and muted everybody's lines, but no worries on that. You still can interact with our speaker today. And in terms of interacting with today's speaker, you can ask your questions via the questions panel anytime throughout the webinar. And then at the end of the presentation, we do have some time set aside for questions for our speaker to answer them. So feel free to ask or type any questions that come to mind throughout the presentation, and we will try to get to as many of those at the end of the presentation as time allows today. Today's webinar is one of many in our upcoming Veolia Water Tech Talks program that will happen throughout the year. If you are interested in signing up for any additional webinars, please feel free to go over and register over at www.veoliawatertech.com. On the screen, we've got listed a couple of the upcoming ones, so feel free to go over to that site, check out the upcoming schedule, and we'll be adding to that often, so check back often as well. Additionally, we've made available our collection of on-demand webinars that we've conducted over the last few years. You can also access those 40+ on-demand webinars over again at www.veoliawatertech.com. So feel free to go over to the website, browse the topics to see if any of those are of interest to you. One other housekeeping note is that we've got a PDF participation certificate that will be sent to you via email after the webinar, and you should receive that within 1 to 2 days or so of that webinar. And then also at the end of today's webinar, you'll receive a quick survey requesting your feedback. Should take no more than 20 or 30 seconds of your time. And for those of you who do complete that survey, you'll be entered into a chance for a drawing for a $25 Amazon gift card. So if you'd be so kind as to fill that out for us, we would greatly appreciate that. Now, before we hop into our main part of the presentation today, if you're not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider. And we offer clients a variety of technologies, services, and project options. So you can learn more about that over on our website, or feel free to reach out to us after today's webinar to learn more about our capabilities. And we support our clients in a variety of different markets as well, a variety of industrial markets, municipal markets, and so on to help support their water and wastewater needs. And with that, now I'd like to introduce our speaker for today's presentation. Sudhakar Viswanathan is responsible for developing biosolids and bioenergy projects for Veolia. He has a master's degree in environmental engineering from Syracuse University and has varied experience in roles that include research development and industrialization, product management, and more recently, business development. Sudhakar has more than 20 years of industry experience and has authored more than 30 technical papers. And with that, I'd like to now turn it over to Sudhakar for our presentation today.
Thank you, Jill. And I hope the folks on this webinar can hear me well. I already got a couple of texts from friends saying that the audio was not coming through very clearly. So I hope it was just some internet thingy that's going to go away. I'm actually going to pause my webcam during the presentation, so you're not distracted with me being animated on it. But I'm going to pop back the video during the question and answer session, so that you can interact better with me at that point in time. So I'm going to switch my webcam off and go ahead with the rest of the presentation. So the agenda for today's webinar is pretty much as listed here. We are going to touch briefly on PFAS because even though it's a hot topic, not everyone is familiar with what PFAS is, and just we'll quickly touch on where it is and if it's in our sludge and such. Then we'll focus on a specific technology that we are using to address this contaminant in our sludge, and of course the research that supports our work, and we are going to present some results, and we are going to close it with some summary as well as Q&A from the audience. Quickly on PFAS. So for those who are not familiar with this compound, there are close to 5,000, or depending on who you ask, maybe even 6,000 of these compounds that have been in use since 1950s. So folks have been using this for various applications, mostly for industrial application, but also in consumer products. For example, it's in the most popular ones I would imagine is something like a Teflon. So everyone's got a pan at home that has Teflon coating, which makes it non-stick. So this is a very popular polymer application of PFAS compounds. But then there are many others that we don't even know exist. For example, dental floss is covered with PFAS as well. But again, the use of this compound is almost endless. It's in everything that is either rainproof, non-stick, or non-scratch, any of those things, but also in other applications like firefighting, because this is resistant to heat and such. Now, why are we talking about a compound that we have had since 1950s or so is because as we learn more about these compounds, we are finding out that these compounds could potentially be carcinogenic. These compounds were built to be a forever chemical. In other words, built to resist physical or chemical changes. So they really, chemically, they're some of the strongest bonds that you'll find. And of course, knowing it's a carcinogenic, it's also toxic, and it's a known endocrine disruptor. So depending on how much of it is in your system, it could potentially have some health considerations. It also bioaccumulates. So it's very similar to what we traditionally know for other compounds like mercury, or rather other elements like mercury. So it bioaccumulates. What it means is you could be consuming it at a really small rate or at a large rate, depending on how much you cook with your Teflon ware, but you're accumulating those compounds within your system. So it doesn't get flushed out very easily. There are some studies out there that says that some of these compounds could have a half-life within your body up to 12 years. So that's, that is from when you stopped using it. So it's a pretty tricky compound. So the question that people mostly ask when when I'm out and about, talking about this issue is PFAS in my sludge? So everybody's like, is it in my sludge or is it a regional thing? So if you look at this map, which is from ewg.org, they do a very good job of updating this map. So this is from Jan 2021. So this is a new map, so relatively new map. That's again, 3 months old. So here we are looking at the military sites which have known PFAS contaminations or high levels of PFAS. You superimpose that with your drinking water and then other known sites. So this could be like an airport or an industrial site. Now, if you look at this map, and if you're joining this call from, say, Wyoming, you're going to be thinking, there's no problem in Wyoming. Look, there are no dots on Wyoming. So that must be the place to live. But that's not necessarily true. This map only has data from facilities that have made this information public. In other words, if you look at this map from 2020, before December 2020, North Carolina looked like a great place to live, which is where I live, because there were no dots on it. So not having a dot does not mean you don't have PFAS in your drinking water or in your sludge. It only means that it has not been reported and it's not in the public domain. So if you look at the map today, obviously North Carolina is all covered in green. That's because in December 2020, that data was made public. So this map was updated since. So you can see there's a lot of dots. So if you're in a state that is currently showing no dots, it only means that your state has not either quantified it, or if they did, they haven't reported it. That's what it means. In short, there is PFAS in almost every part of the world where we have industrialized, where we are using things like Teflon or even fast food. So it's everywhere. So it is in your sludge. Now, if you break down the PFAS compounds into within the wastewater system, because we are talking about the wastewater industry, if you look at those various compounds, and if you want to generally classify them as to where each of those compounds end up, broadly you could call them into, categorize them into three groups here. But what you're going to see is most of the terminal compounds, most of the precursor compounds, these are compounds that are not fully formed. They tend to be hydrophilic, so they like the liquid part of the wastewater. And the terminal compounds, which are fully formed compounds, they don't like liquid, so they're hydrophobic. So they like to stick to things, so they end up in solids. So because we are going to be talking about PFAS in sludge, what we will be dealing with is mostly those terminal compounds. Now, what's the difference between each of them? It really only means that a terminal compound is far easy to be identified or quantified in laboratories, because that's what the analytical capabilities are right now. So if you have to figure out all of the precursors that are in the matrix of thousands of PFAS that's out there, you need to do what's called the total oxidizable precursor, or the top assay, which basically oxidizes the precursors into terminal compounds and then quantifies them. But you can't really break them down into individual compounds like P4R, PFOS, simply because that's not the nature of the top assay. Now, there was a recent study, I think this was Jan 2021, GWI had a press release, which a colleague was kind enough to share with me. She sent this information. So you can see here, they estimate, this is based on GWI's estimate, they're going to spend close to $4 billion to address PFAS in drinking water between now and 2026, which is 5 years. So in the next 5 years, GWI estimates that the utilities in the US alone, this is not Canada or Mexico or anything, it's just the US, they're going to spend $4 billion to address PFAS. And now you may be wondering, what those options are, and that's not necessarily covered in this presentation, but there are a couple of liquid side treatment options that Veolia has that you can check out on our website. In general, if you're concerned about this being in your drinking water, the best thing to do would be for you to just pick up the phone and call your local drinking water plant and ask them for the data. And as a ratepayer, you should be able to get that information. And I surely did for my town here. So that brings us to the next question. So how do you destroy this PFAS, right? This is built to be indestructible. This is a forever chemical. You can cook on it. So obviously, it's got some thermal resistance. So how do you break it down? So we are not the first ones to ask this question, obviously, because you can see here, there's a couple of papers from 2003 or earlier where others have attempted to do the exact same thing. And you can see in this one study that EPA and 3M, they were taking pure PFAS, PFOS, and they were combusting it at some degrees, in this case 600 degrees or so, and they were basically seeing if there's any degradation, and if so, does it form any other gases and such. So there were other studies. We didn't cite all of them here, but there are other studies that looked at potentially pre-treating the waste with some known stabilizing chemical, lime or whatever the case might be, to see if they can further reduce greenhouse gas and such. So we took these studies as a basis for our work, because we rather than just starting from scratch and shooting in the dark, we thought we'll just look at what others have done, see what we can take from that, and improve on those studies and apply that obviously to the wastewater industry where we're dealing with sludge, which tends to be a little more complex because we are not burning pure PFAS compounds. It's in a sludge matrix, so there's some other things that you need to deal with, just more than just having to worry about the PFAS destruction itself. So with that, we looked at the thermal processes as an option. We also did look at chemical treatment, but that's something that we are not pursuing at this time. We do have some options for chemically treating, oxidizing sludge, but we just don't think it's going to be a feasible solution for a marketplace, which usually tends to select technologies that are affordable. So we looked at all the thermal reduction technologies that are out there. This graphic is from GWI, so I thought, might as well show what's out there. And the reason I have all of this listed here is because you can thicken the sludge, you can pre-treat it with THP even, you can digest it, you can dewater, you could even dry, and you still won't get rid of the PFAS. You're not going to be, none of those processes going to matter. The nutrient recovery column clearly is not even going to be in play. We are going to focus mostly on thermal reduction, but I have included indirect thermal drying in our study because we wanted to have drying as the first step before we do some thermal reduction, because we have found that incineration of just wet cake is not necessarily the best way to go about it. So with that being said, under the thermal reduction category, we looked at incineration. We also looked at supercritical water oxidation, and we looked at a couple of emerging technologies, or stuff that's out in the marketplace that are entering the thermal reduction marketplace, like gasification and pyrolysis. We happen to get lucky because we are pretty close to Duke University in the Triangle. They have a supercritical water oxidation plant, a small plant, 1 MGD plant at the university, which they could take sludge and run experiments and such. So that's just an option that we got lucky for being geographically in a place where we had some access to it. So with that said, we looked at those 4 technologies, and we are basically, this table is just giving a quick comparison as to what is similar and what is not. And as you can see, many of these technologies can go up to certain temperatures. So, some are more restrictive, some can only operate between, 14 to 1600 for in the instance of a conventional incinerator, whereas something like the Biocon ERS, which is what we ended up using for this study, has a much wider range. You'll also notice some of these technologies require pre-drying. So for example, for an incinerator and the supercritical water oxidation, they could just take dewatered cake, so say 25% or so, and they're able to treat that. Whereas pyrolysis gasification, as well as the Biocon ERS, you need to pre-dry the sludge so as to get rid of all the water. That's where it performs best. And again, the challenge with having just dewatered cake in an incinerator is more than just the implication on PFAS destruction. It has to do with the volume of flue gas that you're going to generate, because it's going to have all this water and steam that gets carried out of the system, making the process complex, because we are going after some compounds that are basically at detection limit in most instances. So you don't want to have to compound the problem by having excess flue gas as well. So most of the studies that's out in the public domain at the time of our study was basically talking about how PFAS can be removed from the primary matrix, right? So in the case of incineration, when you burn the sludge, you end up with ash. If you test the ash, in many instances, they didn't see any PFAS, or any of those PFAS compounds. With the same thing with the supercritical water oxidation as well as the pyrolysis. The primary output is water and char, and if you just focus on that, they did show some removal of PFAS to a great extent, 90, sometimes 3 logs, sometimes 2 logs. Same thing with the case of our own technology, the Biocon ERS, but we were not satisfied with the idea that just the ash part has no PFAS, but we also wanted to know, does the PFAS end up going in any of the liquids in the water part, which we use for air pollution control, or in the condensate, or whatever the case might be, or does it come out in the emission once the combustion is done? Because those are critical, because if it were up to me, I would leave the sludge with PFAS as is, rather than burning it and taking the PFAS and now putting it out in the emission. You're better off to not do anything if you're doing a shoddy job when you're dealing with incinerator. That's our philosophy. So we really wanted to study in depth to see what the implications are. Now, just to give a quick overview for those who are not familiar with the Biocon ERS, it's basically a dryer in combination with a furnace. So we take sludge, dry it with the dryer, and we get it up to Class A biosolids. So theoretically, you could stop there and people can use the biosolids as a biofertilizer. But in our case, we are going after PFAS, so we are going to combust it at high temperature in an ERS. And basically, the flue gas is then captured in a sequence of heat exchangers and other economizer and such. And you're reusing the heat that's coming off of the flue gas to power the dryer. So once you have the system going, once you have both the dryer and the ERS functioning, you don't need any more fossil fuel to get the system to run. It's self-sustaining energy-wise. It doesn't matter if it's digested sludge or undigested sludge or whatever the case is, because we are drying it up to more than 90% dry solids. The sludge autogenously combusts within the furnace, so there is no need for fossil fuel. So this is a very sustainable process. And in the past, we just used it for energy recovery. That's where the name ERS comes from. It's energy recovery system. So it's really not anything fancy. It's just an energy recovery system that we have now optimized for PFAS destruction. So again, just to quickly touch on what it is, it's a step-grade biomass furnace. So it's not a new technology by any means. It's very common in colder climates like countries like Canada, or if you go to Scandinavia, like Denmark, Finland, and Sweden and such. There they have so much wood chips, basically wood chips and sawdust from the timber industry. They use that as the primary fuel. They're not going, even though they have tons of natural gas and fossil fuel, they just take the leftovers from their timber industry and they basically use that as the fuel. So you could actually go visit wastewater plants in Scandinavia, and they may be even producing steam using these types of furnace. I've actually been to a thermal hydrolysis facility up in the middle of nowhere, Sweden, and they were using this exact system, to basically take wood pellets and they were burning it and producing steam for use in the thermal hydrolysis process. So it's a pretty cool technology. Again, nothing new. It's just something that we like because it has features where we can adjust how long the solids and the gases need to be within the system. That gives you the flexibility to control and optimize the process for breaking down those complex PFAS compounds. The research, again, we focused on taking what we know and applying that on a laboratory scale. And again, the reason we wanted to do it in a laboratory scale is twofold. One, none of the full-scale plants wanted us to go and throw in PFAS into their sludge, whether they had it or not, and they did, but they just didn't want to do that because there's too much of a risk, because you're emitting directly to the atmosphere when it's all said and done, and they didn't want to take a chance by contaminating the air that's being currently emitted up. And two, there was always this lingering question as to, if you did it in a full-scale study, what happens if PFAS does come out of the sludge, and what if it ends up sticking to the walls and the ducts in the within the ERS or in the duct lines that's going into the air pollution control system? And you may still not measure anything in your emission, but that does not mean you have successfully destroyed PFAS. You just converted it into something else that's now stuck to the walls, and maybe 10 years from now it'll break through, and next thing you know, you are contaminating the air in the around the facility. So we decided we want to do in a controlled environment such that we can actually even clean or wash the insides of the reactor so that we can capture anything that could potentially stick to the wall. And again, we did the study in a couple of phases. We self-funded it so that we don't, because our intention was to commercialize this solution. And here's a quick setup. Setup looks kind of boring because it just looks like a big box with something sticking to it. But if you look at the schematic, there's a quartz furnace that we can control the temperature of. And we have all this option to add excess air, or we can add nitrogen, we could add any other type of fluid to the system, and then we could introduce the sludge either in a batch format or in a continuous format. And then we had all these other options to wash the system fully, so that we are even considering if there's any PFAS that hits the wall and stays onto the wall, we can clean that out and capture everything in impingers. So we are able to do both analysis on the liquids as well as the solids. So this was a perfect setup for us, and we collaborated with the University of Dayton. So they are contract researchers, and we have hired them to do the work for us. And one of the reasons we chose that particular university is because all of the studies that were done in the past, the 2003 study or the 2013 study, all of those studies basically pointed us to this research institute, because they were the same folks who were running those studies for EPA as well as 3M and such. So we thought these guys already know what they're doing, so they must have some prior knowledge to help us with the setup. So that way, again, we are not reinventing the wheel. We are just taking everything that's available, which is not much, but still maximizing the output from it without having to spending a whole lot of time just struggling to figure things out. But that doesn't mean it all went smooth, and I'll cover that in the next few slides. So typically what we would do is we take sludge, dry it up to 90 plus degrees, and so we have our own methodology for us to do that in our lab here in the Raleigh Triangle area, and we do that and we send it to those folks. They then place it in a sample boat, like in the second picture, and they insert it into the furnace. So in this case, we removed all the insulation just to take photos, but that's not how it is in the real world. And on the other side, again, we remove the insulation just to see if there's any soot formation or anything. You know when you are not getting treatment if that photo does not look like, you can't see clear through those quartz tube, and if you see black smoke or anything else, it's not working. So again, what we noticed was if we have low oxygen, like in a paralytic condition or in a gasification type of level, we were having soot formation and other issues, which basically, ended up with very low PFAS reduction. So in a way, we also learned that some technologies don't really work, or does not work as well. And in this case, the impinger that I'm showing here is one of those times when things didn't go well, and you can see it's fully covered in soot. That's because it's one of those failed scenarios where the oxygen concentration was not high enough. And final photo is basically of the inert material. So if you burn dry sludge like what we have, dried sludge, which is at 90% or so, you're going to end up with something like what you're seeing here. Although you see the volume looks similar, in terms of the mass reduction, that's about 60% reduced mass. So typically about 40 to 50% of your sludge is inert material, dry sludge, that is. We had quite a few challenges. I don't want to spend too much time here because in the interest of time, I'm going to keep moving forward. But so some of the challenges we had were included just finding and identifying locations. People were, we knew the plants that had problems, but when we asked for sludge, even though we signed NDAs and such, they were pretty hesitant to participate because they were afraid that that information will get out and people would know that they have issues. But we did finally manage to get a couple of good locations and get sludge. We had to spike sometimes just to get a higher enough concentration. We had other problems, which again, all of these challenges were overcome, but they're explained in our paper. We pre-published it in 2020, which is not a complete paper, but we are hoping to have it published in a journal sometime by the end of 2021. But again, the multiple problems, but we managed to overcome almost all of them, with the exception of maybe the fluoride balance, which I'm not even sure if it's possible, and we may abandon that part of the study. Just a quick update on the progress. So in phase 1, we did about 5 or so transport efficiency studies. So that just gives you an idea of how accurate your data is going to be. If you're able to capture all of the PFAS that's going in, that and if you do the mass balance, does it all come out, and things of the nature. So we kind of we took our time to get that part figured out, and of course phase 2 is where the meat of the experiments are. That's where we are studying low temperature combustion, high temperature combustion, and then various other conditions which mimic or simulate what happens in the PFAS, and that way we get all of the efficiencies narrowed down. And we also are continuing the study is still ongoing, so we are still continuing the work to see if there are additional steps that we could include within the study to simulate maybe air pollution control technologies like a scrubber or a mercury removal step, which we think is going to be necessary for this type of an application. With that, some quick early results. Here, we had to verify volatilization of PFAS, because there are studies out there that shows that you can volatilize PFAS under some temperature conditions. So because we use a pre-drying step, We wanted to make sure that none of those compounds, none of the known compounds were coming out of the solid phase or the liquid phase into the gas phase. And so we had to do some of those verification studies and just to fine tune the dryer model. And then, of course, we did the calibration model. This is where all of the data that we ever got, we basically used them. And of course, the first thing is, we wanted to see at what temperature. So the T99, or what they used to call in the old days, the incinerability index. It's a mouthful, so we just go with T99. So basically, that tells you at what temperature 99%. It's just a 2-log reduction or breakdown of the compound is. But what we learned is, some of the big compounds break easier, but they form smaller chain compounds. So we had to do multiple studies. So here we are showing about 24 compounds that we studied. And let's see, let me see, I can click into this one maybe, and yeah. So yeah, we have redacted some information here only because, this is an information that we use in our model, so we didn't want to have this out in the public domain. But so our studies were mostly various conditions of temperature, oxygen concentration, chemical concentration. So, the sludge with more PFAS or more of this particular compound or less of them. And then we subject it to various conditions to basically get an idea of what happens in the time frame, within 4 or 5 minutes. That's basically what we're looking at. Yeah, or 2 or 3 minutes, because it's a combination of what happens in the sludge phase as well as in the gas phase. We took an average and came up with this idea. So basically what we're doing with it is we take this information and we use it to fine tune the ERS. So we know the ERS works because it's pretty flexible. Now it was reversing the knowledge to see, should we add more air? Did we do it underflow? Do we do it overflow, and all those things? So that's where the next part of the study was. So just to give a quick high level, so the info on what we have since done is, we have over 24 PFAS compounds is what we have studied. Now, as analytical techniques improve, the labs probably are able to detect more terminal compounds. Right now, they can only do 24. We use 24, but I heard just a week or so ago that they added 2 more compounds or 3 more. So maybe that's something that we may have to repeat. But if the compound's close enough and if we know the properties of it, maybe we don't have to. Now, just to give an example, we had a couple of those compounds. We were able to easily get 99.9, so 3 log. But then, there are some smaller compounds or small chain compounds which are much harder to get to. But then, our goal was we do all this and we still meet the SSI standards that's required for combustion technologies. So with that, this is just a summary slide. Our current model, we are able to optimize our ERS. So we are able to provide this as a fully industrialized solution, because this is not the first time we'll be doing it, but it'll be catered towards PFAS. So we are able to do PFAS reduction, PFAS treatment using thermal oxidation based on the ERS model. We also believe that air pollution control is going to become a key here, because these temperatures are much higher than what you typically see in your incinerators, conventional incinerators. But because we are dealing with PFAS reduction, we focus more on the ability to destroy PFAS as opposed to just being a low-cost solution. So the air pollution control is still going to be a predominant cost in your solution. And just a quick note, cautionary note from our study, what we noticed is incomplete combustion, the amount of PFAS that you're able to destroy, especially in the gas phases, were very low, and that risk is much greater than just having to leave the PFAS in the sludge. That's basically our conclusion. With that, I'm going to open up my webcam so that when I'm answering your questions, you get to see me. I'm open for questions now.
Yeah, Thank you very much, Sudhakar, for that very informative presentation. Just to remind everybody, feel free to type in your questions over in the right-hand side questions panel. And with that, we will kick off our Q&A. First question here that we've got, Sudhakar, that came in is just talking a little bit about this process addresses PFAS in sludge. So what happens exactly to the PFAS in water?
Okay, yeah, that's a good question because I think I tried to cover that earlier in the presentation. So if there is liquids in your sludge, for example, in a conventional incinerator, that adds to the complexity of the flue gas being wet. In our case, we are removing all of the water in the dryer, so we are not dealing with as much water in our sludge. Now, with that being said, that liquid still has to get treated somewhere. As I showed in our earlier slide, a lot of the precursor compounds end up being in the liquid matrix, which means they have to eventually get treated, or as they go through the wastewater process, especially in secondary treatment, they get oxidized and they show up in the final effluent. We do have a couple of technologies within Veolia, and those technologies are based on either ion exchange or GAC, granular activated carbon. Those are filter-based technologies, basically absorbing this compound so that we are removing it from the water. And if you visit our website, you will, or you could just Google PFAS treatment, and you should see within the first page or so PFAS treatment wastewater or sludge. You will see within the first page, you should see us. And we have a couple of solutions for it, and we are constantly researching and adding new media to our portfolio so that we can address the liquid treatment as well.
Great, thanks. Another question is, of the options available to remove PFAS in sludge, do any of them allow for biosolids to still have beneficial reuse?
So I think this question is stemming from this white paper or concept that's been presented from someone else. We don't have the technology, but the idea was gasification or pyrolysis. They end up with this material called char, biochar. Some people call it biochar, similar to biosolids. But basically, it's carbon that's left over that could potentially be used for agricultural and other types of scenarios. But if you are dealing with, if your primary objective is to get rid of PFAS, then the challenge becomes whether that char is of value, because then you end up with a whole lot of other issues related to PFAS. So the short answer is no. You're not going to have, at least as of today, unless the chemical treatment option somehow is cost feasible, the answer is no.
Okay, I think we've got time for maybe a couple more questions here. One of them is, can you skip the dryer and just incinerate the sludge in the furnace?
Oh, I mean, is it physically possible? Yes, it's physically possible if you have dewatered cake to combust within the dryer system. I'm sorry, within the ERS system. But then, you know, there's two issues. One relates to the amount of water that's in your sludge, which is going to add to the volume of flue gas and the wetness of the flue gas. And number two, you're not going to have the benefits of energy neutrality. For example, with the Biocon ERS system, the total amount of energy that you're going to use for both of this either of this process is going to be zero once you get it going. So the energy neutrality part or the energy positivity part goes away. So it's doable, but it's probably not economically feasible.
Okay, I think maybe one or two more here. What was the PFAS removal rate in the thermally treated biosolids?
So in the biosolids, it was non-detect. That's what our target was, always to not have any PFAS. In fact, I'm an idealist, so if you ask me, there should be no PFAS in any of the 3 phases, in water or in the air. But in the real world, that's not how it works, right? No technology is able to get you 100%. I mean, if somebody claims that to be the case, then I would buy it, but I would not. To be honest, if you're getting 3 log removal under low concentration inputs, that's a good number. With a high concentration input, you can get 6 log, but that still won't make any sense. So rather than focusing on the log removal, we focus on the concentrations. They can go down to picograms, but to expect the collective 5,000 compounds to end up with a number that's in the picograms is going to be unrealistic. Nanograms, maybe.
Okay, I think we've got time just for one more question here. What is the smallest and largest plant this process can be used at?
Okay. There is no range, but there are limitations by the inherent nature of the way the system is. It's a combination of a belt dryer and a furnace. So if you go too small of a facility, the economics of the process may not look as favorable because you're spending a whole lot of money, and maybe a regional facility could be a better solution on those small 1 MGD plant type of a scenario. But our smallest plant is in the 2.5, 3 MGD range, but they don't operate this facility 24/7. They run for 6 weeks and turn it off for 4 weeks, turn it back on 6 weeks. So they're not getting as much energy recovery, but when they're running for the 6 weeks, they're not using any energy. So that's those types of options are still possible. On the flip side, the larger the facility, because we are using belt dryers tend to have a lot of footprint. The bigger the facility, you just end up having massive dryers that are as long as a football field. And again, then the question becomes, do we have room to put this facility? Because larger facilities tend to be in bigger cities, which also have the more expensive real estate costs. So there's a fine balance. But if you're in the 5 MGD to 40 MGD range, I think that's a sweet spot. And if you look at all the wastewater plants in the US, that probably accounts for 13,600 plants. So most of the plants in the US can use it.
Great. Well, thank you very much, Sudhakar, for that very informative presentation today. Unfortunately, we have hit our time mark. So in the interest of time, that will conclude the webinar today. However, if we did not get to your question, we do apologize for that, and we'll follow up with you afterwards for that. One thing that I forgot to mention as well, this webinar today was recorded, so you will be receiving a recording of that at the conclusion as well. And with that, I do wanted to remind you, as soon as this ends, if you would please remember to take the survey, that would be greatly appreciated. And we do thank you very much for your time. And if you enjoyed this Tech Talk today, please feel free to check out our upcoming series. And with that, that will conclude today's presentation. Thank you.
Thank you.